In abstract algebra, the symmetric group Sn on a finite set of n symbols is the group whose elements are all the permutation operations that can be performed on n distinct symbols, and whose group operation is the composition of such permutation operations, which are defined as bijective functions from the set of symbols to itself. Since there are n possible permutation operations that can be performed on a tuple composed of n symbols, it follows that the order of the symmetric group Sn is n. Although symmetric groups can be defined on infinite sets as well, this article discusses only the finite symmetric groups, their applications, their elements, their conjugacy classes, a finite presentation, their subgroups, their automorphism groups, and their representation theory. For the remainder of this article, symmetric group will mean a symmetric group on a finite set. The symmetric group is important to diverse areas of mathematics such as Galois theory, invariant theory, the representation theory of Lie groups, and combinatorics. Cayley's theorem states that every group G is isomorphic to a subgroup of the symmetric group on G. Definition and first properties. The symmetric group on a finite set X is the group whose elements are all bijective functions from X to X and whose group operation is that of function composition. For finite sets, permutations and bijective functions refer to the same operation, namely rearrangement. The symmetric group of degree n is the symmetric group on the set X equals 1, 2, n. The symmetric group on a set X is denoted in various ways including Sx, X, sigma X, and Sim. If X is the set 1, 2, n, then the symmetric group on X is also denoted Sn, n, sigma n, and Sim. Symmetric groups on infinite sets behave quite differently from symmetric groups on finite sets, and are discussed in, and this article concentrates on the finite symmetric groups. The symmetric group on a set of n elements has order n. It is abelian if and only if n2. For n equals 0 and n equals 1 the symmetric group is trivial, and in these cases the alternating group equals the symmetric group, rather than being an index 2 subgroup. The group Sn is solvable if and only if n4. This is an essential part of the proof of the Abel-Ruffini theorem that shows that for every n greater than 4 there are polynomials of degree n which are not solvable by radicals, i.e., the solutions cannot be expressed by performing a finite number of operations of addition, subtraction, multiplication, division and root extraction on the polynomial's coefficients. Applications. The symmetric group on a set of size n is the Galois group of the general polynomial of degree n and plays an important role in Galois theory. In invariant theory, the symmetric group acts on the variables of a multivariate function, and the functions left invariant are the so-called symmetric functions. In the representation theory of Lie groups, the representation theory of the symmetric group plays a fundamental role through the ideas of Schur functors. In the theory of Coxeter groups, the symmetric group is the Coxeter group of type n and occurs as the Weyl group of the general linear group. In combinatorics, the symmetric groups, their elements, and their representations provide a rich source of problems involving Young tableaus, Plactic monoids, and the Bruhat order. Subgroups of symmetric groups are called permutation groups and are widely studied because of their importance in understanding group actions. Homogeneous spaces, and automorphism groups of graphs, such as the Higman-Sims group and the Higman-Sims graph. Elements. The elements of the symmetric group on a set X are the permutations of X. Multiplication. A group operation in a symmetric group is function composition, denoted by the symbol or simply by juxtaposition of the permutations. The composition Fg of permutations f and g, pronounced f of g, maps any element x of x to f. Concretely, let applying f after g maps 1 first to 2 and then 2 to itself, 2 to 5 and then to 4, 3 to 4 and then to 5, and so on. So composing f and g gives a cycle of length L equals km, taken to the kth power, will decompose into k cycles of length m. For example, verification of group axioms to check that the symmetric group on a set X is indeed a group. It is necessary to verify the group axioms of closure, associativity, identity, and inverses. 1. The operation of function composition is closed in the set of permutations of the given set X. 2. Function composition is always associative. 3. The trivial bijection that assigns each element of X to itself serves as an identity for the group. And 4. Every bijection has an inverse function that undoes its action, and thus each element of a symmetric group does have an inverse which is a permutation too. Transpositions. A transposition is a permutation which exchanges two elements and keeps all others fixed. For example, is a transposition. Every permutation can be written as a product of transpositions. For instance, the permutation G from above can be written as G equals. Since G can be written as a product of an odd number of transpositions, it is then called an odd permutation, whereas F is an even permutation. The representation of a permutation as a product of transpositions is not unique, however. The number of transpositions needed to represent a given permutation is either always even or always odd. There are several short proofs of the invariance of this parity of a permutation. The product of two even permutations is even, the product of two odd permutations is even, and all other products are odd. Thus we can define the sign of a permutation. With this definition, is a group homomorphism. The kernel of this homomorphism, i.e., the set of all even permutations, is called the alternating group n. It is a normal subgroup of Sn, and for n2 it has two elements. The group Sn is the semi-direct product of an and any subgroup generated by a single transposition. Furthermore, every permutation can be written as a product of adjacent transpositions, that is, transpositions of the form. For instance, the permutation G from above can also be written as G equals. The sorting algorithm bubble sort is an application of this fact. The representation of a permutation as a product of adjacent transpositions is also not unique. Cycles. A cycle of length k is a permutation f for which there exists an element x in 1, n, such that x, f, f2, fk equals x are the only elements moved by f. It is required that k2 since with k equals 1 the element x itself would not be moved either. The permutation h defined by as a cycle of length 3, since h equals 4, h equals 3 and h equals 1, leaving 2 and 5 untouched. We denote such a cycle by, but it could equally well be written or by starting at a different point. The order of a cycle is equal to its length. Cycles of length 2 are transpositions. Two cycles are disjoint if they move disjoint subsets of elements. Disjoint cycles commute, e.g., in S6 we have equals. Every element of Sn can be written as a product of disjoint cycles. This representation is unique up to the order of the factors, and the freedom present in representing each individual cycle by choosing its starting point. Cycles admit the following conjugation property with any permutation. This property is often used to obtain its generators and relations. Special elements. Certain elements of the symmetric group of 1, 2, n are of particular interest. The order reversing permutation is the one given by. This is the unique maximal element with respect to the Bruhat order and the longest element in the symmetric group with respect to generating set, consisting of the adjacent transpositions 1in-1. This is an involution, and consists of transpositions, so it thus has sign, which is 4 periodic in n. In S2n, the perfect shuffle is the permutation that splits the set into two piles and interleaves them. Its sign is also. Note that the reverse on n elements and perfect shuffle on 2n elements have the same sign. These are important to the classification of Clifford algebras, which are aperiodic. Conjugacy classes. The conjugacy classes of Sn correspond to the cycle structures of permutations, that is, two elements of Sn are conjugate in Sn if and only if they consist of the same number of disjoint cycles of the same length. For instance, in S5, and are conjugate, and are not. A conjugating element of Sn can be constructed in two-line notation, by placing the cycle notations of the two conjugate permutations on top of one another. Continuing the previous example, which can be written as the product of cycles, namely, this permutation then relates and via conjugation, i.e., it is clear that such a permutation is not unique. Low-degree groups. The low-degree symmetric groups have simpler and exceptional structure, and often must be treated separately. S0 and S1. The symmetric groups on the empty set and the singleton set are trivial, which corresponds to 0, equals 1, equals 1. In this case the alternating group agrees with the symmetric group, rather than being an index 2 subgroup, and the sign map is trivial. In the case of S0, its only member is the empty function. S2. This group consists of exactly two elements, the identity and the permutation swapping the 2 points. It is a cyclic group and so abelian. In Galois theory, this corresponds to the fact that the quadratic formula gives a direct solution to the general quadratic polynomial after extracting only a single root. In invariant theory, the representation theory of the symmetric group on 2 points is quite simple and is seen as writing a function of two variables as a sum of its symmetric and antisymmetric parts. Setting Fs equals F plus F, and Fa equals F minus F, one gets that 2F equals Fs plus Fa. This process is known as symmetrization. S3 is the first non-abelian symmetric group. This group is isomorphic to the dihedral group of order 6, the group of reflection and rotation symmetries of an equilateral triangle. Since these symmetries permute the three vertices of the triangle, cycles of length 2 correspond to reflections, and cycles of length 3 are rotations. In Galois theory, the sign map from S3 to S2 corresponds to the resolving quadratic for a cubic polynomial, as discovered by Gerolamo Cardano, while the A3 kernel corresponds to the use of the discrete Fourier transform of order 3 in the solution, in the form of Lagrange resolvents. S4. The group S4 is isomorphic to the group of proper rotations about opposite faces, opposite diagonals and opposite edges, 9, 8 and 6 permutations of the cube. Beyond the group A4, S4 has a Klein for group 5 as a proper normal subgroup, namely the even transpositions, with quotient S3. In Galois theory, this map corresponds to the resolving cubic to a quartic polynomial, which allows the quartic to be solved by radicals. As established by Lodovico Ferrari, the Klein group can be understood in terms of the Lagrange resolvents of the quartic. The map from S4 to S3 also yields a two-dimensional irreducible representation, which is an irreducible representation of a symmetric group of degree n of dimension below n-1, which only occurs for n equals 4. S5 is the first non-solvable symmetric group. S5 is the Galois group of the general quintic equation, and the fact that S5 is not a solvable group translates into the non-existence of a general formula to solve quintic polynomials by radicals. There is an exotic inclusion map S5-S6 as a transitive subgroup. The obvious inclusion map Sn plus 1 fixes a point and thus is not transitive. This yields the outer automorphism of S6, discussed below, and corresponds to the resolvent sextic of a quintic. S6, unlike all other symmetric groups, S6 has an outer automorphism. Using the language of Galois theory, this can also be understood in terms of Lagrange resolvents. The resolvent of a quintic is of degree 6. This corresponds to an exotic inclusion map S5 S6 as a transitive subgroup, and while this map does not make the general quintic solvable, it yields the exotic outer automorphism of S6. See automorphisms of the symmetric and alternating groups for details. Note that while A6 and A7 have an exceptional Schur multiplier and that these extend to triple covers of S6 and S7, these do not correspond to exceptional Schur multipliers of the symmetric group. Maps between symmetric groups other than the trivial map Sn1 S0 S1 and the sign map Sn S2. The most notable homomorphisms between symmetric groups, in order of relative dimension, are S4 S3 corresponding to the exceptional normal subgroup V less than A4 less than S4, S6 S6 corresponding to the outer automorphism of S6. S5 S6 as a transitive subgroup, yielding the outer automorphism of S6 as discussed above. There are also a host of other homomorphisms Zm-Sn where n greater than m. Properties. Symmetric groups are coxeter groups and reflection groups. They can be realized as a group of reflections with respect to hyperplanes Xi equals xj, 1i less than jn. Braid groups Bn admit symmetric groups Sn as quotient groups. Cayley's theorem states that every group G is isomorphic to a subgroup of the symmetric group on the elements of G, as a group acts on itself faithfully by multiplication. Relation with alternating group. For N5, the alternating group N is simple, and the induced quotient is the sign map, an SNS2 which is split by taking a transposition of two elements. Thus Sn is the semi-direct product in S2, and has no other proper normal subgroups, as they would intersect in either the identity, or in N. Sn acts on its subgroup and by conjugation, and for N6, Sn is the full automorphism group of an AUTSN. Conjugation by even elements are inner automorphisms of N, while the outer automorphism of N of order 2 corresponds to conjugation by an odd element. For n equals 6, there is an exceptional outer automorphism of N, so Sn is not the full automorphism group of N. Conversely, for N6, Sn has no outer automorphisms, and for N2 it has no center, so for N2, 6 it is a complete group, as discussed in automorphism group below. For N5, Sn is an almost simple group, as it lies between the simple group and its group of automorphisms. Can be embedded into by appending the transposition to all odd permutations, while embedding into is impossible for generators and relations. The symmetric group on n letters, Sn, may be described as follows. It has generators and relations. One thinks of as swapping the ith and th position. Other popular generating sets include a set of transpositions that swap one and I for two in, and a set containing any n cycle and a 2 cycle of adjacent elements in the n cycle. Subgroup structure. A subgroup of a symmetric group is called a permutation group. Normal subgroups. The normal subgroups of the finite symmetric groups are well understood. If N2, Sn has at most 2 elements, and so has no non-trivial proper subgroups, the alternating group of degree n is always a normal subgroup, a proper one for N2 and non-trivial for N3. For N3 it is in fact the only non-identity proper normal subgroup of Sn, except when n equals 4, where there is one additional such normal subgroup, which is isomorphic to the Klein 4 group. The symmetric group on an infinite set does not have an associated alternating group. Not all elements can be written as a product of transpositions. However, it does contain a normal subgroup S of permutations that fix all but finitely many elements, and such permutations can be classified as either even or odd. The even elements of S form the alternating subgroup A of S, and since A is even a characteristic subgroup of S, it is also a normal subgroup of the full symmetric group of the infinite set. The groups A and S are the only non-identity proper normal subgroups of the symmetric group on a countably infinite set. For more details see or maximal subgroups. The maximal subgroups of the finite symmetric groups fall into three classes: the intransitive, the imprimative, and the primitive. The intransitive maximal subgroups are exactly those of the form sim times sim for 1k less than n. 2. The imprimative maximal subgroups are exactly those of the form sim wr sim where 2kn, 2 is a proper divisor of n and wr denotes the Reith product acting imprimatively. The primitive maximal subgroups are more difficult to identify, but with the assistance of the Onan-Scott theorem and the classification of finite simple groups, gave a fairly satisfactory description of the maximal subgroups of this type according to Solow subgroups. The Solow subgroups of the symmetric groups are important examples of p-groups. They are more easily described in special cases. First, the Solow p subgroups of the symmetric group of degree p are just the cyclic subgroups generated by p cycles. They are of equals such subgroups simply by counting generators. The normalizer therefore has order p and is known as a Frobenius group and is the affine general linear group AGL. The Solow p subgroups of the symmetric group of degree p2 are the Reith product of two cyclic groups of order p. For instance, when p equals 3, a Solow 3 subgroup of sim is generated by A equals and the elements x equals, y equals, z equals, and every element of the Solow 3 subgroup has the form xgil for 0 I, j, k, L2. The Solow p subgroups of the symmetric group of degree Pn are sometimes denoted Wp, and using this notation one has that Wp is the Reith product of Wp and Wp. In general, the Solow p subgroups of the symmetric group of degree n are a direct product of I copies of Wp, where 0 ip-1 and n equals a0 plus pa1 plus pk-ac. For instance, W2 equals C2 and W2 equals D8, the dihedral group of order 8, and so a Solow 2 subgroup of the symmetric group of degree 7 is generated by, and is isomorphic to D8 times C2. These calculations are attributed to and described in more detail in. Note however that attributes the result to an 1844 work of Cauchy, and mentions that it is even covered in textbook form in Transitive Subgroups. A transitive subgroup of Sn is a subgroup whose action on 1, 2, n is transitive. For example, the Galois group of a Galois extension is a transitive subgroup of Sn, for some n.